Welcome back, everyone. Let's start our morning session today. The first speaker is Piljin from KAIST to tell us about anomalies and probability molecules.
All right, thank you very much. Good morning, everyone. As I was finishing this slide, I realized that there's nothing to do with the supersymmetry. So on that excuse, I added sort of second half that does touch on supersymmetry. But this is about gauge theory, really. Gauge theory and fermion anomalies. So what else could it be? The main thing I wanted to talk about is, again, very old stuff. And by the way, during the pandemic era, I found myself regressing in time. 10 years, 20 years, Sungju there, we work on some 20-year-old things. Now I'm back 40 years. I'm back in early 1980s. So some of the things I'm going to talk about today, if I were a very good student, I should have understood back then, 40 years ago. Apparently, I was not a good student. So I tried to sort of bring it back the memory and try to address this a little bit better than I had done in the past. And along the way, maybe you can catch a couple of new things as well. Now, so we love gauge algebra, right? By the way, when I write something like this, this is always algebra, not group. So I'm not going to touch on the subtleties with the discrete division, SO versus SO3 versus SU2, etc. That's entirely different thing. There are a lot of things I want to talk about there, but not today. So what are the differences between this? Classical, exceptional, of course. But there are other ways to classify these things. Simply laced and not simply laced. So one of the earliest things we learned. This is probably less trivial to students, but this sort of related to this, simply laced and not simply laced. This is Langland dual, self-dual. They are dual to each other. So supersymmetry people, of course, all know this. And what is this difference? SP and the rest. So since I said anomaly, you should realize what I mean is, of course, written anomaly. So only for SP, this fourth homotopy group is non-trivial, it's Z2. And you have all the rest, this is trivial, and this is really reason why we have this discrete gauge anomaly on the large gauge transformation as discovered by Witten 40 years ago. But this last one maybe is not that trivial to you. Anybody can guess? No? I mean, I really learned this only a year ago, actually. I mean, I computed related things. I realized this is the case. This difference you can actually find if you go through, not Wikipedia, and you have to do some computation, or at least work with this Lie algebra routine that in Mathematica that everybody use, and play with it. The answer is thinking indices. So thinking indices is some integer that characterized by the representation. And in typical situation, this thinking index turns out to be, they are of course always integer. And by the way, one definition of thinking index you will see in various places this. But of course, this is actually dependent on the normalization of the root. So mu of R is the highest weight of the your representation, and this rho of G is the celebrated Y vector, is half sum of all positive root. So this gives you some integer, but of course this is normalization dependent because you need to sort of set your convention of what is your normalization of root. Turns out the one well motivated by physics choice is to set this thinking index for joint representation to be twice to a zeta number. And when you see dual Cox-eta number, you should immediately think about instant, right? So what this thing translates physics-wise is if you are given a unit instanton and as f(h)(f) in a given representation and integrate over, upstairs is always integer, downstairs is always even integers. So this difference between this classification between SP, SU versus SO may not be that familiar to you. Although you have seen this in famous paper by Witten, for example. If you go back about 10 years ago, there was this, the second paper, I think, by Witten on holography. And he was discussing various gauge theory in 4 dimensions in the presence of oriented fold. And he was discussing about difference between this oriented fold and that oriented fold, and pointed out there is a factor 2 difference in the periodicity of data. So sometimes it is, they say there is 2 kinds of SP theory, but that's not quite right because it's simply a statement that this is period 2 pi, data is, here is period is 4 pi, but the way that's realized in string theory is a little bit funny because there's single type 2 bit data angle that's responsible for data here and data there. And what happens is that there is a discrete Z2 flux you can turn on. And that way, from the string theory viewpoint, it looks like you have 2 kinds of SP theory. But in reality, at least in field theory setting, all that means is that periodicity of data doubles. Okay? But I mean, anyway, so that's when I define this in the defining representation. So it's really a statement of defining representation in these classical groups. Those of you who are Chern-Simons person, you have seen this factor 2 elsewhere. For classical group, when you do defining representation, quantization of K is integral, except there is a factor 2 in SO side. So this was one of the things that really confused me early on when I was trying to study Chern-Simons theory. But of course, the 2 are obviously related. So with this in mind, let us go to actual problem or actual review of this Witten anomaly, which is exclusive property of SP theory in 4 dimensions. So Witten asked the following question 40 years ago. Suppose we have SU2 theory and we have a single fermion, massless fermion, chiral fermion. So it's a 2-component fermion rather than 4-component fermion. In each case, you do, say, for example, Euclidean path integral here. But this is not for the 4-component, but rather 2-component one, because this L is left moving. But since Dirac operator has this off-diagonal shape, there is no eigenvalue problem on its own. It's only if you elevate this to non-chiral and complete this 2, add something there as well, we have well-defined eigenvalue problem. So at the end of the day, that partition function is actually not determinant, but rather Pfaffian of this Dirac operator. So this, you have eigenvalue here lambda, and then you would have eigenvalue here lambda as well, or minus lambda. That's probably a better way of saying it. So because of there is no well-defined eigenvalue problem in this chiral case, in some sense, you reduce the degree of freedom by half relative to Dirac. So it's really determinant of this Dirac operator, but square root in some rough sense. So that's where Witten started his question. As I said, it's actually Pfaffian you are computing. So what you are supposed to do, he teaches us, is think about the fact, remind yourself the fact that in even dimension, this chirality operator flips the eigenvalue. So it always comes in pairs, lambda and minus lambda. So it gives you a natural way of computing this Pfaffian, or square root, by multiplying all or half of the eigenvalues. Say, let's decide that we will take only the positive ones because it's always lambda and minus lambda. Then he asked, oh, is that something we can do consistently? And the, of course, answer was no, otherwise he wouldn't have written it. So it's always lambda and minus lambda like this. And if I imagine some one parameter family of this 4-dimensional problem and making it 5-dimensional problem, on each of these 4-dimensional slices, I can have this Dirac eigenvalue problem. So as lambda and minus lambda. And what we are supposed to pick up is only positive one. But imagine continuously changing this. And since your Dirac operator is changing continuously, lambda will dance. And sometimes this eigenvalue will cross. And something like this happens. So, but I mean, if it is just generic deformation, of course, I'm changing the problem. So I'm having, different Paphian at the end of the day is no surprise. But the problem is in some cases, when you have this pi of 4 force homotopy group of gauge group non-trivial, sometimes you can make initial end and the final end related by this pi 4, the force homotopy group. And he asks, since even if it is large gauge transformation, it is gauge transformation, nothing should change under that. So if you identify the first and the last, do you get the same answer? And obviously, if I have one of the eigenvalue crossing like this, right? Instead of this, you need to use this, otherwise it would be not consistent. In between, it's not gauge transformation because it's not continuous gauge transformation. And that configuration, he gave the name mapping torus. Maybe somebody else gave that. So what happens is you started out with product of these two, or infinite number of them. And one of the eigenvalue crossed because of this large gauge transformation you did. And then, of course, you will have a flip of sign. So your partition function, which should not be aware of large gauge transformation, flips a sign on the large gauge transformation. And that's called anomaly, because your partition function is supposed to be something physical. And then one goes on, ask exactly when that happens. And according to what he was writing down, of course, it can happen only if the homotopy group, force homotopy group is non-trivial, and that happens among various Lie groups, simple Lie groups, only for SP. And simply stuff which is SU2, and therefore we call it Witten's SU2 anomaly. Okay. So, getting down to, this is fine, but given a configuration, given spectrum, when does that really happen? It might be that this happens even number of times, in which case -1 times -1 is 1, so nothing bad happens. So it requires to understand when this odd number of eigenvalue crossing happens. So he asked this question, and of course the answer has to be that, because only for that case you can have non-trivial large gauge transformation. Now, when you have something like this, and let's imagine taking this fifth direction as something physical, and think about Dirac fermion in this 5 dimension. What happens to the Dirac operator in 5 dimension? And the one thing you can figure out rather quickly is that if I have 4-dimensional mode with lambda whose eigenvalue behaves as a function of this direction, and if eigenvalue sign flip its sign like this or this, what happens is that you get a single normalizable mode because of this exponential factor. Okay? So depending on whether it's crossing that way or that way, what happens is that you get chiral or anti-chiral. But of course, in 5 dimensions, I mean, we don't have chirality in 4-dimensional sense. So by chirality, you should, I mean, maybe I shouldn't have said chiral. And then Witten goes on and say, let's compute this. I don't know how he computed this back then, but that's the answer he got for SU2 isospin S representation. For each of those, we'll give this many eigenvalue crossing. These are all integers. You sum them up. If it is odd, you are in trouble. If it is even, you are okay. So that was the answer. But actually, when I was reading this first, I had no idea how he computed this. Anybody know this? I mean, this is supposed to be, this is supposed to be so-called eta invariant of this 5-dimensional configuration, this what he called mapping to us. And it's unlike, ITR single index, there is no local expression you can integrate and obtain this solution. But somehow he managed to get this number. And that will tell you if I have a, I think, I guess S equal half is fundamental. I guess, do I get odd really? All of a sudden I'm confused. I think it should be. Anyway, but then there was a sentence in that paper in the middle. Just right after he write down, he noticed this. And what was this? This instanton zero mode in the representation. For some reason, instanton has some relevance to this story, even though, as you remember, instanton is configuration that's created by large gauge transformation, but not pi 4. It was created by pi 3. Nevertheless, there is a relation like this. It's a single sentence in his paper. I was completely puzzled by this. Why does this happen? Did he know something else? But he didn't say anything there. Anyway, so that brings me to the question. I mean, we already know this happens only for SP theory. But in the higher dimensional SPK, what is the relevant quantity? It might be that that's the right quantity. And in the end, it turns out that's the right sum of thinking in this of whatever your fermions. So let me step back and ask about how do we really compute this mode 2 number? So it's eigenvalue crossing, mode 2, or is normalizable zero mode counting, mode 2. Either way is a rather challenging problem, I thought. So the problem is something like this. You have some, for example, let's simplify things such that you have M3 n time, Euclidean time. Okay. I don't think it has need to be that. It's just simplifying assumption. And then I will add one more direction, fifth direction, along which this eigenvalue flow would happen. So this end and that end would be related by large gauge transformation of this kind. And then ask in this context, what is the eigenvalue crossing number, or what is number of zero mode in this configuration? So whatever is in the middle cannot be pure gauge because it's large gauge transformation. So in some sense, you may call it, mode 2 instanton of some kind in one higher dimension. But remember, this thinking index was relevant for 4-dimensional instanton. So then you can see why that was really the case by the following construction. This was brought to my attention by my collaborator, Chang Jia. There is well-known mathematics construction. I don't know if this was, I don't know whether this was something that Witten knew about, and that's how he was able to do this or not. But there was no mention of this anywhere in his papers, in that paper and thereafter. So again, let us think about the simplified situation with 3 manifold of Euclidean time, and then this mapping torus direction, Phipps direction. And what we are asking for is how do I get this large gauge transformation on the pi 4? How do you construct something like that? And apparently instanton has something to do with it. The answer is, it turns out, I'm writing this in the case of SU2. Okay, that's why I have sigma 3. You have, what you want to do is create the instanton, okay, between left and right. So this U is the pi 3 large gauge transformation rather than pi 4 large gauge transformation. But that's not what I want. What I want is pi 4 large gauge transformation. There is Pontryagin term construction is much more general than this, but it's applicable here. In such a way, what you do is from bottom to top, you do the following twist along sigma 3. So if I take any slice, it's just 4-dimensional manifold with the instanton sitting there. But along the Euclidean time, you do this simple twist. And you can show, and Tom Pontryagin showed, that this is exactly what's needed to construct or elevate this pi 3 winding to pi 4 winding. So this is construction in SP1 or SU2 or SO3. Now, what's this got to do with this observation that this counting problem, eigenvalue crossing counting problem, has something to do with the instanton in 4 dimension? You can sort of think of, I guess I should have had this sigma 3 change it to I3, meaning isospin. The same thing, actually, sorry about that. Suppose I have fermion in fundamental representation, okay? And say defining representation of this, let's say this is SPK or SP1, to be more specifically. What this thing does, this operator, okay? Because this is half integral thing in the defining representation, it acts exactly like 1 over minus 1 to the f. So when I try to find the 0 mode counting of this, you will be doing some sort of counting with this inserted. But what this does along this direction is turn fermion into periodic boundary condition, as you are all familiar. So once I have this setup, what happens is 0 mode of this instanton translate immediately 0 mode of the entire configuration because of periodic boundary condition. Okay. So this is the reason why, this is the reason that underlies Witten's one sentence statement that you can do this 0 mode eigenvalue crossing counting, which should be actually some eta invariant in mapping torus. But actual computation one does, at least I do, is this. And that explains why this happened. Yes?
So where does Pontryagin Tom come from?
Oh, this construction itself goes by the name of Pontryagin Tom. It's a little bit more general than this. It's about...
is it special for relating constructing pi 4 out of pi 3 just for compact groups? Or?
I think it's much more general statement. We just applied it here. Yeah.
You can use the same construction for different homotopy groups, like pi 2 and pi 3.
Maybe, I don't know actually.
So it's some general construction.
Yeah, general construction. Yeah. It's general construction that comes in the homotopy theory early on, apparently. I didn't know about this at all. As I said, Chiang-Jia found this. I don't know where you find it. Where did you find it? Oh, textbook. Very good. Something I should have known.
So you are using -1 step on the right side. What about left side?
Oh, it's the same because it's not left side I do this. It's everywhere I do the twist. On the left, it doesn't matter because it's trivial.
Well, tau dependence, how it became the -1 step, and tau becomes 1. That thing is -1 step.
Tau becomes 1. What do you mean? Tau is this,
Right.
0 to 1.
Right. So it's depending on tau, but
Right.
-1 step is not depending on tau.
No. So this is the boundary condition. This periodic boundary condition that translate to -1 to the f. Once you go, if you do the Hamiltonian formulation along that as time, that's all that happens. I was so happy to learn this actually.
So the one previous one is a dimension of representation times second Casimir.
What? Oh, you mean this answer?
Yeah.
Well, this is the. So if you are given some field, fermion field content with isospin S, when I say isospin, of course, mean SP1. We translate this, but this is much more general statement. So forget about the left-hand side. If you are given any SP gauge theory, okay, this is the answer. Now, of course, you might wonder how specific this construction is to SP, because other than SP, this shouldn't give you any non-trivial thing. So in fact, I can start here with 2x2 SU2 construction of this kind and embed it in SUN instead. And what happens there is that that's actually not, you can show that it's not topologically stable. And then there is a related statement, in this case, how the mode to index in this mapping torus exists. If you go to SU side, mode to index do not exist. And usually in odd dimensions, so index doesn't exist, but sometimes you can get mode to index out of it. Anyway.
But the sum over the Vinken indices, that's true. That still works for any
I think so.
representation.
That's right. That's right. That's
It
right.
just so
It's
happens
just
that the
they have,
answer is only ever be odd when it's SP.
right. So that's where I'm coming to, in fact. This is the reason I showed you SP and SCO2 are on the same side, right? Again, going back to Witten's, I learned so many things from Witten's papers, some later paper by Witten in Communication in 1985. Actually, talk about this fact that the instanton zero mode counting is related to not this detail, but just the fact that this happens to be the case. He does make use of it and say the following things. Forget about pi4 and suppose you have an instanton in your theory. It could be Yang-Mills instanton, it could be some other kind of instanton too. But in the case of Yang-Mills theory instanton, the thing that he points out is that if you find odd number of fermionic zero mode, you are in trouble for very different reasons. So that's the actually not, I mean, Witten wrote this in 85 communication paper, but he attributed to Jeffrey Goldstone. Apparently, Goldstone pointed out this. Imagine having a situation, so I'm looking at now four-dimensional physics. I mean, X disappear. And let me think about the following funny combination of large gauge transformation. You do large gauge transformation at some particular slide, then undo it later. So that's creating an instanton and anti-instanton. But in between, you rotate, this is spatial rotation, rotate the first large gauge transformation. So two large gauge, opposing large gauge transformation, but rotate spatially the other one. And if I just think about instanton contribution, of course, Yang-Mills theta angle comes in and cancel itself, should be 1. On the other hand, if this happened to create odd number of fermionic zero mode, and since I'm only rotating spatially this guy, that will pick up sign because fermion on the 2 pi rotation acquire sign. So in fact, in that case, when phi is 2 pi, this is -1, which is mutually inconsistent. So there's something funny about situation where non-perturbative process is accompanied by odd number of fermionic zero mode. And you can sort of think of it as, for example, when we do dilute incidental gas approximation, we are accustomed to replacing this by some non-perturbative vortex. But if you have a fermionic zero mode, that vortex cannot exist on its own because Grassmann path integral, fermion path integral will kill it immediately. So what you have to do is insert several fermions. So if you have a single fermionic zero mode, you have a single fermion inserted in that vortex. But if that happens, how do you even complete Lorentz invariance if you have one? Maybe if you have three, maybe you can do it somehow. I cannot quite imagine how to do that. But even if you are succeed in doing this, the vortex, the term in the Lagrangian is going to be Grassmannian. I don't know how to think about that, in fact. But this is not by itself, I think, immediately an inconsistency issue. In this case, this can be constructed by this funny sort of bi-layer two large gauge transformation. This is clear, but in other dimensions, in other processes, which is not accompanied by this large gauge transformation, actually it's not that clear. For example, I can easily imagine a quantum mechanics situation where I could have a single fermion attached Hamiltonian. That's like raising operator. So I think it's a little bit more detailed dynamical question, but nevertheless, it makes you very uncomfortable. And in 4 dimensions, this does happen. There is an issue. But logically, the two problems seems different kind of issue. They are both sign issue. It's not clear whether two sign issues should be really connected. In this case, of course, this is connected by this, happen to be.
So this thinking that appears in instanton zero mode count?
Yeah, that's exactly instanton zero mode in the representation you choose.
I haven't seen it before. I asked you, I think, I guess I haven't seen it.
Well, I haven't seen it either, actually. You know, I'm writing a book and I spent about 2 months to get down to this formula at the end of the day. Go through all the normalization issue.
I learned about Piljin index a couple of years ago for some different.
Taking yes everywhere, of course, these days. So one of the most important, but one thing I want to emphasize that this is not normalization dependent thing once you normalize it by dual Cox-Theta number for the joint.
Why you want to normalize this to your Cox-Theta number?
Because I want instanton physics. This physics motivated really because I don't know. I mean, you remember this one that involves the bivector? That's of course normalization dependent. That expression you can use if you normalize the largest root to have length square 2. That's when, if you use that, you will get integers every time.
The other thing is when I have monopole and if I have fermion in zero mode, it doesn't make it a fermion, it's a boson. And instanton is
there is a very subtle difference between fermionic zero mode when it comes to soliton and instanton. I don't have a slide here, but I was initially very confused by that too, because we know solitons that has single fermionic zero mode, Jacob-Levy and all that story. Euclidean path integral treat zero mode very differently than the Lorentzian. So there is a potential confusion there. Trust me, I addressed it. I'm not going to talk about it today. Anyway, Jesus. There is an issue. So let me remind you this. On one side, I was talking about pi 4. On the other side, I was talking about instanton fermion zero mode. And why did I show that stupid slide early on, classification of Lie algebra? Because of this, SUN. So for SUN and SP, number of zero mode for the instanton can be odd. For all others, that doesn't happen. On the other hand, this Witten anomaly happens only for SP. It doesn't happen to SU because it doesn't have right homotopy group. So what in the world is happening with SUN theories? I said, if this become O, that's inconsistent. That is potential inconsistency. And there was a relation between the two in SP theory. But what's happening with SUV theory? Very simple answer, it turns out. One main difference between SP and SU in 4 dimensions is SP, you don't have any anomaly polynomial, it's identically 0 because of its structure. SU, of course, you have anomaly everywhere, perturbative anomaly. So I asked, what if I require this anomaly polynomial cancel among all the fermionic spectrum that requires representation? There's one single requirement on the representation. Is that strong enough to make sure sum of Dink index to be even? And amazingly, this does happen. I'm not going to show you the numbers, but we can sort of check this for arbitrary fundamental representation and how that works for tensor product of those fundamental representation, and you can show rigorously that does happen. So in that sense, Witten was entirely correct, of course. Not that I ever doubted. SP theory is the only theory that's potentially problematic in 4 dimensions, in this sense. Now, then problem arises for me, yes?
What about spin groups that have a symplectic spin group?
Oh, none of this depends on the group, Lie group. It depends only on the algebra. Because it's local physics, I'm not thinking about, I mean, you could have some additional issue, I would imagine, if you have in your space-time 2 cycles, then we know the thing, funny things happens because of distinguishing group rather than distinguishing algebra. Everything is about algebra at this moment. So space-time doesn't have any 2 cycle, and that precludes everything. That's actually a good question. I was thinking of asking that question. I haven't done it yet. So what happens, this was entirely field theoretical setup. So as long as we impose the perturbative anomaly cancellation, Witten's story flies straight, nothing odd happens, right? But in string theory, that's not all. Sometimes you get in string theory, field theory that is actually anomalous at 1 loop level. But anomaly inflow come to the rescue, so the entire string setup is again consistent. And this is one of the examples where so-called fractional D3 probe theory that probes what we know as F1 geometry. And it comes with this funny quiver theory of this fractional D3. It's really individual node represents some combination of D7 and D5 wrapping 2 cycles and 4 cycles, producing a fractional D3 numbers. And as you can see, N1, N2, N3, N4 could be really anything you would think. So if I have, say, N1, 3, N3, 1, 0, rest, I'm in trouble. This is SU times U1 theory. And if I have an instanton process here, I'll be in trouble. Does that really happen? It shouldn't really happen because but I mean, once I have that, of course, this N1 theory is anomalous, right? Or this is also anomalous. So as a field theory, 4-dimensional field theory, it doesn't exist. It exists only in the context of string theory. Nevertheless, if reality couples down to field theory modulo this anomaly inflow, I need to answer this odd number of fermion question, even though there is no large gauge transformation issue. We sat on this for about a year. We'll come back to this slide later because I asked Ami yesterday. So maybe, I don't know. Never mind. So, but this fractional brain configuration with D5, D7 wrapping compact cycle in Calabi-Yau is a little bit too complicated for me. So what I did instead is find easier problem, which is entirely field theoretical. The way things are going, I'm not gonna get into supersymmetry. Anyway, let me fly through the, I mean, the seniors, for young people, I think you really need to study the setup by Yonekura Witten. This is one of the motivation I'm trying to show you this. There is sort of this very interesting setup given by Yonekura and Witten about 5 years ago. It's about topological insulator thing and trying to realize massless fermi on the boundary by starting with highly gapped theory in the bulk. And by imposing particular boundary condition, this has something, again, this has something to do with how 5-dimensional fermion behave in terms of eigenvalues of this four-dimensional Dirac problem. And because of this, you end up with highly peaked boundary mode here. If you send mass of this 5-dimensional fermion to infinity, that way you realize a version of topological insulator. Highly gapped here, and the massless fermion here. And let's see. At the end of arduous computation, what they show is the following fact. Suppose I compute partition function of this entire setup, 5-dimensional massive fermion. The two pieces that come in, one, let me skip all this. One is the boundary contribution. And this boundary contribution, even though this comes from I mean, it's not really boundary contribution alone. It has something to do with this particular boundary condition you impose. At the end of the day, what happens is eigenvalue of this the boundary fermion get producted and give you essentially determinant of Pfaffian of that massless fermion. So this is kind of object you would see in the Witten computation. On the other hand, there is a contribution from this bulk very massive fermion, and that bulk contribution turns out to be nothing but APS, eta invariant that's computed under APS boundary condition. I mean, the process is rather long-winded, but it's very instructive, so I encourage young people to actually go through the paper. Mine like so much. So this happened. So I mean, eta invariant showed up in recent in our community in the context of topological insulator a lot, and this is actually one of the aim they were aiming with this example is to realize the topological insulator a little bit more concretely. And in fact, this actually was later developed by IPMU group to address higher form, discrete version of higher form symmetry. So that's another very interesting application of this. But at the end of the day, what happens is that you have eta invariant here, you have partition function, absolute value of partition function on this boundary fermion. Okay. Now, for eta invariant, I probably had a slide somewhere over here. Eta invariant is this formal infinite sum of sign of eigenvalue, which should be, of course, regulated in a certain way, like this. Oh, I forgot zero mode counting there. Sorry about that. So it's entirely gauge invariant thing because eigenvalues are gauge invariant things no matter what. So this partition function is gauge invariant. On the other hand, remember I said how you end up with massless fermion. I probably forgot to say it's actually massless chiral fermion you get. So if I have SUM theory with a single massive Dirac fermion here in 5 dimensions, you get with 4-dimensional chiral fermion in the same representation, which should be, of course, anomalous, perturbatively anomalous. So this is the way you see at the end of their paper, but there is alternate way of saying this. Yeah, let me skip all this. This is of course related to width index as well. But the thing that I want to point out is this eta invariant in order dimension has this well-known relation to Chern-Simons action, but they are not the same. I mean, people, I think, in the community, Chern-Simons community, confuse. They should be computing this, but rather they talk about this. There also there's a bit of confusion in the community for a couple of decades. But in this situation with the boundary, you have these three pieces. And Chern-Simons density is, of course, small invariant of the small gauge transformation if it is compact. But if it is not compact, because it produces boundary term, it's actually modular boundary term is invariant. And it's famously not gauge invariant the large gauge transformation. On the other hand, the left-hand side is always gauge invariant no matter what, because it's constructed out of eigenvalues. So structure is such that Chern-Simons piece exists as a continuous part, and there is a bulk part, which correct this large gauge non-invariance of large gauge transformation, and there is a boundary piece that correct this failure on the small gauge transformation. Okay. So another way of writing exactly the same thing is this. Instead of eta invariant, I put Chern-Simons and the rest. And what happens is the boundary massless fermion on the boundary would generate this partition function with potential sign. But since this is chiral, this part is going to be perturbatively anomalous. On the other hand, you have this Chern-Simons piece, and this is exactly Chern-Simons piece you find in the process anomaly descent. Okay. So what happens? Entire thing is gauge invariant. Boundary piece is gauge non-invariant, but there is inflow part can generate out of bulk. So this is one purely field theoretical setup where perturbative anomalies cancel no matter what. Even if the chiral spectrum here is completely arbitrary, because of there is always relevant factor arising here because of this bulk massive fermion by construction that takes care of perturbative anomaly entirely. So in this toy model, I should emphasize this is a toy model because the real problem I want to solve is this general string theory setup. Is one example where perturbative anomaly is not canceled by spectrum, but by inflow. And then we are back to the same problem. Are you going to have a problem with the instanton? And this is, if I'm starting with SUN theory, because there is no forced homotopy group of that, there is no large gauge transformation issue. Okay, but instanton issue is still there because spectrum is chiral. Answer to that is kind of trivial, I'm afraid. I was hoping that this will teach me something that I can use in string theory setup. It's a little bit too trivial. Simple as this. Instanton is four-dimensional, co-dimension four thing. So in 4 dimensions, it's a point-like thing. But we are thinking of 5-dimensional extension. So I can think of following two situations. You do the Yonekura-Witten setup with one end closed like this. I try to write down instanton, but it becomes instanton string. It has to go somewhere. Where does it go? It cannot go anywhere, but come back itself. So it always shows up as instanton, anti-instanton pair. So odd number of fermion is zero mode. Issue is cancelled by odd number of fermion attached here. You could do the other one, we just cut up on the other side with two boundary. Same thing happens, it's a string. So instanton becomes string, it's a one-dimensional object. And although I was a little bit fast about how this boundary fermion occurs out of this bulk massive Dirac fermion, there's a chiral massless fermion appearing here. There's chiral, anti-chiral massless fermion occurring there. So again, it sort of resolved itself completely. So that was a little bit anticlimactic, I'm afraid. Back to the real problem. So I asked Ami yesterday. He gave me an answer, and I thought about this, and I decided I don't agree with it. So Ami raised very important issue that I haven't really thought about in detail. That is, this configuration, when I say fractional D3, what I really mean is D5, D7 wrapping 2 cycle, 4 cycle, and combine in a very complicated way. So it's like brains intersecting brains, or brains ending on brain, not quite ending on brain. So there could be potential tadpole issue on the world volume, right? For if you have, say, D3 brain and D string ending on it, that's fine. It's actually monopole from the D3 viewpoint. But if you try to compactify the D3 on something compact, that's not acceptable configuration because it's like the Gauss law wouldn't be obeyed. Okay. But to see this in actual geometry is kind of nightmare, and I don't see how that might come about. But the reason I didn't agree with that is because I can use exactly the same quiver diagram not as fractional D3, but fractional D0. And the relevant problem is called word crossing problem. And some of you know I've been working on word crossing problem for 10 years. For there, I don't really have any sort of restriction on possible. And this tadpole issue would be in the Calabi-Yau direction. So I'm a little bit confused at the moment. Exactly. I mean, I was imagining at some point, although since this is a situation where anomaly is not really canceled, I mean, honestly, I cannot say decoupling here. So potentially there is a logical possibility of fermion string theory, the non-field theory fermion in higher dimension, suddenly producing additional zero mode and resolving the issue that way. I don't know whether that's the case here or not. So this is still ongoing. It has been ongoing. I'm almost ready to give up, unless some of you tell me what the answer is. Okay, so that's first half. Sorry about that. Second half, let me just show you the answer. So this, I mean, I don't know, some of you might remember about 6-7 years ago, there was this hoopla that's originate from Britain somewhere, claiming that supersymmetry has anomaly. Okay, I was very intrigued by that. And one of those people, Ioannis, happened to be with me. So with Ruben, we went through exactly what the hell is going on in this so-called anomaly of supersymmetry. And along the way, I discovered something, again, something I should have known 40 years ago. Not 40, I'm not that old, 30 years ago. Anyway, that's standard word identity stuff, okay? I don't need to show this slide. And then this is standard BRST stuff, how you do the anomaly descent given an anomaly polynomial. I don't need to show this, I think. And that's the solution. So that's, you go back to Badin and Jumino paper in 1984, that one of the most beautiful paper in the anomaly literature. So that's the answer. You start with anomaly polynomial of some type like this. This is computed by Witten and Alvarez-Gomez comprehensively. You follow Badin and Jumino and say this is the anomaly. And that way, of course, anomaly, so-called best-Jumino consistency condition like this, and which tells you immediately that anomaly cannot be gauge invariant observed. This gauge, it transforms non-trivially under gauge transformation. I'm now talking about small gauge transformation. Sorry about that. Large gauge transformation has passed us. I'm a little bit more mundane textbook stuff. So that's the standard story. And then if you go back to Badin and Jumino, they also tell you how one might elevate this non-gauge invariant anomaly expression to gauge invariant one by inventing so-called Badin-Jumino current. This is something, again, you isolate starting from the anomaly polynomial. LA is for some reason called antiderivative. I think it's a Stora who apparently found this set of relations. Very interesting history there, actually. And in say, standard four-dimensional anomaly polynomial, the Badin-Jumino current looks something like this. It looks very similar to Chern-Simon, but it's not same as Chern-Simon. It's something else. So you can sort of, by adding that thing to your consistent current, what we call consistent current, you can make its divergence to have this form, which is covariant thing. But of course, if one vanishes, the other vanishes. That's why we usually do not care about it. But when it comes to word identity, sometimes you need to care about the detailed form. And the part I didn't understand 30 years ago, and now I understand, is diffeomorphism anomaly is rather different from the gauge anomaly. I mean, these days, of course, when somebody asks what diffeomorphism anomaly, what you really do get is local Lorentz anomaly. The two are not the same. They are equivalent in the sense if one vanishes, the other vanishes too, because they share the same anomaly polynomial. But the way they appear in the word identity is a diffeomorphism anomaly that appears. And the difference is because diffeomorphism anomaly, diffeomorphism transformation is actually not just rotation. It's not just gauge rotation, but translation plus gauge rotation. Anyway, so because it's a space-time transformation, one thing that you have to be careful about is that if you put in external gauge field that coupled to would be conserved current, that also transform under this diffeomorphism. So when you write down word identity, left-hand side, right-hand side. Right-hand side is anomaly, left-hand side is variation of your action, expectation with respect to whatever transformation. Left-hand side acquires additional terms because of this in case of diffeomorphism. Okay. So anyway, let me skip this. Diffeomorphism is a little bit funny relative to gauge transformation. It has usual gauge part, but it has translation as well. So for some reason, this seems this Christopher connection is much more natural than spin connection in this story, by the way. But at the end of the day, the reason we do not care about it or we are not that aware of this is because the answer you write down at the end of the day follows exactly the same pattern as the gauge anomaly descent. So just forget about the translation part. You just imagine it to be just this gauge transformation and you get the right answer. And again, this is from Badin and Jumino 40 years ago. Now, with that in mind, and I already mentioned that you get this additional piece in case of diffeomorphism, but there's something funny about this. On the right-hand side, the anomaly you actually get, gravitational anomaly, is gauge invariant on the internal gauge transformation. T mu is, of course, gauge invariant on the internal gauge transformation. But the thing that you generate here, this is not gauge invariant if there is anomaly associated with J. This is, of course, not gauge invariant. Okay? It's a funny situation. Well, of course, the answer has to be that even though I write it this way, there is a way to rewrite this into gauge, manifestly gauge invariant combination, and answer is this. What happens if you start here and know about anomaly of this J, there is a gymnastics you can do, which was done about 10 years ago, actually, by, this paper, I think is the first who did this. you can rewrite everything in a gauge invariant way. Okay. Now, what happens with supersymmetry is exact analog of this, it turns out. So if I do supersymmetry and ask about supersymmetry transformation, say, which I denote by epsilon, of course, this is sort of widely known statement that supersymmetry doesn't have its independent anomaly. So in some version, this should be 0. It's really left-hand side that is problem. So if I do not do any sort of gauge fixing when we deal with vector multiplet, exactly the same thing should happen as diffeomorphism anomaly. You have complicated things, all kinds of off-shell things, off-shell partner of A appears here. You combine everything, and just like this happened, somehow that entire expression becomes gauge invariant. So again, conclusion is same. No supersymmetry anomaly, no anomaly of supersymmetry whatsoever. However, that's not how we do supersymmetry, vector multiply. We always impose best terminal condition, which means we break some amount of supersymmetry by going on shell, partial on shell. And how does that manifest? Again, this is 40-year-old thing. So everybody forgot about this actually. Several years ago when these British people found this or discovered this, they didn't know about this. So what the thing you need to do in the best terminal gauge, we do the best terminal consistency condition, which comes down to something like this. And you go through the usual machine, but not the BRST. BRST doesn't work here, but you have to really solve this. And through all the motion, what happens is that you find so-called anomalous term on the right-hand side of this, word identity, which would have been 0 if I were using, if I were not fixing to the gauge, best terminal gauge. You get something like this, and that's exactly Bardeen-Jumin current. So you move this non-gauge invariant piece, and then you have some additional piece that's a gauge invariant. You move to the left-hand side of the word identity, and this get added to current. Something like this happens. So if I were not gauge fixing to best terminal gauge, I don't have any right to keep it here. I need to move everything to the left. So in that sense, it's really same kind of pattern that you see in the diffeomorphism case. So conclusion, no supersymmetry anomaly whatsoever. And then this confused people at some point, and Closet and Pietro Kim actually addressed this in the context. I mean, this really makes difference when you have this external gauge field. For dynamical gauge field, none of this is ever issue, actually. I think some people think it otherwise, but that's wrong, actually. It's issue only if this is a flavor symmetry. Gauge symmetry, this doesn't happen at all. No subtlety there. It's just everything is embedded in here, in that case. And then they sort of follow through in a concrete example how this so-called anomaly affect, but this is actually fact. It does affect something about the partition function. And of course, you know, the partition function people, they put everything, you can couple all the external thing. And this does make a difference in the final answer. So in that sense, it was an important step in the understanding of partition function. And then I was saying something about, I didn't understand the diffeomorphism anomaly. And one reason is the standard BRST mechanism, BRST algebra, does not actually work for diffeomorphism. I realized this while doing this work. And of course, it doesn't work for supersymmetrized version of the, I should say, supersymmetrized anomaly rather than supersymmetry anomaly. Actually, there was some internal fight among authors about the terminology there. Anyway, so if you are curious about this extended version, new version of BRS formulation that address both of this in a very elegant way, I would like to think, be my guest. Thank you.
Is that Yanakura Witten example picture? It looks very reminiscent of the symmetry TFT, you know, the whole
That's right.
language.
That's right.
So can it be reinterpreted in that way?
Yeah. In fact, I mean, as I was saying, that the reason they did this is actually for that. I hijacked it for something else. So, it address topological insulator and all the related issue, all the homotopy issue, all that. So it's very a big framework where you can address. So, for example, Tachikawa and company has used it. There was a follow-up paper by Yonekura, Tachikawa, and some others, elevating all of this to a higher form discrete symmetry, for example. So both of that's really nice paper, I think.
In this case, it's not applying to a discrete symmetry. In the example that you were talking about.
Actually, again, I hijacked it for the perturbative anomaly, but if you look at this is the one that appears in the discussion of topological insulator, parity anomaly, and all that. So their application was on discrete symmetries. I hijacked it for something else.
So maybe related to your comment for the end, but so these UK people, when they say they see some supersymmetry anomalies,
Right.
are they trying to rule out certain supersymmetries by that, or maybe you said some partition function has some structure due to these anomalies?
Right.
So what?
I think I don't know exactly what goal they have in mind. As I was saying, if you are talking about partition function in some complex space-time, it does have an effect in the sense that if you do it naively, if you do not think about this additional piece, and if you insist on best terminal gauge, you will end up with wrong answer. On the other hand, if you are thinking of actual physics, for example, spectrum, nothing happens. For example, all of this, I think, partition function, it does have actual effect. So it is an important piece of the dynamics there, topology there. But in terms of real physics in real world, I don't think it has any consequences. I mean, I guess this, in some sense, anomalous world identity. So you are surprised by having additional term on the other side, but you have only yourself to blame for adopting best terminal gauge. Yeah. In that sense, I don't think there is real world physics consequence. Like, for example, Suzy breaking. I don't think you will see any spectrum that's breaking at the level of spectrum. I think there was some hope that that might happen, but I don't think in the end that was the case. Yes.
I vaguely remember that quote unquote supersymmetry anomaly paper says that it's anomalous, quote unquote anomalous, when trace R cube is non-zero.
Oh, that's R symmetry statement, I think. Yeah. When R symmetry is anomalous, yes. But it's the same thing. So although I said flavor symmetry, where is that? Although I said talk about flavor symmetry, any internal, anything that's not diffeomorphism, or even diffeomorphism actually. So anything goes. But again, as I was trying to emphasize, this was something I didn't realize at the time. I realized only recently. This issue happens for external gauge field only. If you have a dynamical gauge field, that contribution enters the supercharge. It enters the energy momentum tensor in the same way. So it affects only external gauge field. So in that sense, again, it sort of restricts itself to it when it comes to real world physics. Yeah. Yes.
Yeah, I also had essentially the same question, but like, so for example, there are examples of supersymmetric theories where like the Kähler potential, not globally all the time. You have to do one of these Kähler transformations in order to see that your theory is good and supersymmetric everywhere. It sort of feels like it's a very similar flavor where you have to sort of do a supersymmetric gauge transformation to realize, like, essentially you can't work in the same gauge for all your theory.
I'm not sure. I think it's much more mundane than that. It doesn't really, I mean, for example, I didn't say anything about nonlinear sigma model, right? So I think it's much more universal, but much more mundane. It's just that you forgot about the fact that Sumino gauge does something funny, one. And two, maybe you are rushing, you are trying to take the anomaly descent story of Bardeen-Jumino too literally. That doesn't really work. As I was saying, BRST algebra need to be modified. You need to extend your BRST algebra one more time in order to talk about even diffeomorphism already. And supersymmetry is sort of square root of translation. And obviously there is that danger. So I think it's sort of come out of disease of trying to generalize things that you didn't completely understand. But at the end of the day, there is no real mystery, but it's a general lesson. Let's be careful. Let's not rush into conclusion. So they are not incorrect, I should say. Their formula was correct. It's just interpretation. I think there was a little bit hasty interpretation. That's all.
What really happens to the partition function is that there are consequences of the supersymmetry that we can say about the partition function. For example, the holomorphy with respect to certain global parameters that we turn on. And those holomorphy can be, for example, violated because of the analysis that he showed as a result in the
Right.
And also that violation is also very mild.
Yeah,
So,
I think there was early in the history that people forgot about that contribution and use some, I mean, deformation in the partition function people, of course, always claim topological invariant, nothing changed under anything. And that was went a little bit too far. So their contribution, I think it was important contribution to remind us, you better be careful if you do not understand everything that's going on.
any further questions?
Okay.
Thank you.
Thank you.